All right, so I want to move on to the second main area. These are all command injections where you're injecting commands in a high-level language like the Bash command shell or the Windows command shell or Python and or SQL. And here we're going to move into binary injection where you inject raw binary code which you have to execute on the server. So let's start with 201 here. And so once you've got a cloud server, which you probably already have, then you can put in this code. And let me bring it up here. This is buff.c. All right, so what this code does, let me make it big front and center. This code creates a very simple command injection case. So I have a subroutine called VO, and I have a main routine where it starts here. So in the main routine, it asks for your name and reads your name, and then it calls BO with two variables, your name and this command, date. And this subroutine copies the name it got into a variable called N and the command into a variable called C. It then says goodbye to the name and it executes the other one as a command by calling system C. So this here is just like that ping form we talked about earlier, where it executes a command line that came from somewhere else, but the idea of the developer was that command line is supposed to be fixed. The problem is the name is going into a string 200 characters long, and down here it's copied into a string that's only 40 characters long. So here we have one of the simplest buffer overflows, which is, by the way, not the most common or the most deadly, but the most difficult to stop. Even the latest Windows defenses cannot stop this kind of buffer overflow, where all that happens is the name, when it gets too long, it leaks into the command variable. So if you run this program, which I compiled as 32-bit here, then, wait, it's not password, it's buff. All right. What? Thought I compiled it. Oh, buff 32, that's why. Okay, buff 32. All right. So what is your name? My name is Sam. It says, goodbye, Sam, and then it executes the command date. But if my name is much longer, let's just run it here and put in a name of 890. That's 10 characters. So if I put in 30, 40, and then ls, then what happens is it interprets the entire 42 characters as a name and prints it here, but then it takes the last two characters that overwrite the command and it executes the command ls. So now I have command injection again. And if I save that and run it again, I can do the same thing we did with the ping form. I can do who am I here, and it will now do an ls and then execute who am I. So I can inject commands up to 40 total characters of commands here. So it's a simple kind of buffer overflow, a very simple memory corruption attack. And again, you've got a remote server you can exploit and find some flags on it here. So that is a C program that results in the same kind of command injection that you exploited previously. And now let's go to the one which I mentioned before is really the meat of the whole course. If you understand ED202, then you understand the most important thing for this entire course. So let's go through this one. I create a vulnerable program called password. So let's take a look at that, pwd.c. Okay, what this does is it's got a main routine here that calls a routine called test password, and depending on the return value of that routine, it'll either print fail or win. But the test password program asks for a password and then always returns 1, no matter what password you give it, so you always fail. There's no way to win at all. You will never execute this code. But we're going to execute that code by exploiting a buffer overflow. And the reason there's a buffer overflow is because there's only 10 characters available to store the password, but the fgets allows me to put in up to 50. So I'm able to exceed the length of the password, and this is the fundamental problem with C, which is responsible for almost all these memory corruption exploits. C is too close to assembly code. It doesn't have defenses. If you were using a high-level language like Python or Visual Basic, it would not let you do this. If you reserved space for 10 characters and then you put in 50, it would just automatically reserve more space. Only C is so dumb as to let you reserve 10 and then casually let you put in 50, because C is supposed to be fast and efficient, and it doesn't waste any time trying to guess what you meant and warn you when something is wrong. It just says, you're the boss. When you write 50 characters into a string variable, all I need is the start address of the string, and I will then put characters in the next 50 bytes and a null at the end. That's all I'm going to do. And I assume that you must have a plan. You must have made sure that those 50 bytes are available for this purpose and nothing bad will happen. It does not second guess you. So if I run this pwd, I probably called it pwd32. Yes, okay. pwd32 is the 32-bit code. So if I enter a password of foo, it just tells me fail. But if I enter a longer password, there's 10 characters, 8, that'll do, all right. 10 characters is a fail, but if I put in more, like 40 characters, then I get a segmentation fault. So this is bad. Now these parts were the program running as intended, but a segmentation fault means I wrote to data that was not reserved for the use of this program, violating the memory segments, and that is like the syntax error in SQL injection. So that means I have created a condition of memory corruption, which I can now exploit. So let's notice something else here. Notice how it prints the password address, and it's different every time. This is because of address space layout randomization, where it randomizes the location of code in memory every time it runs, and it's a strong defense, but for what we're doing here, I want to turn that off. So to turn it off, I have to do these commands. This will just elevate me to root and then change this kernel variable called randomize VA space. So now it will not be random anymore. So now if I run that program and give it a password, and then I run it again and give it a password, it's now the same address every time. It's no longer randomizing addresses, which is what I want. So in order to debug the program, we need to use a debugger. There are a lot of debuggers available, but I'm going to use the simplest one, GDB, which I like. All the fancy ones just get in the way. By the way, I see a question, am I going to share the recordings with students? And I am. I'll just put them right on the page. And if people are just catching up, next time I take a break, I'll publish some of the recordings so you can go back and look at them. All right, so there's, so let's GDB this thing. GNU debugger in quiet mode just to get rid of an irritating message for password 32. So now it's ready to run, and now I can list the program because when I compiled this code, I used the -G switch. So this code is compiled with symbols, so you can do source code debugging. So if I do list 1 to 13, it shows me part of my source code. And I have a win function down here, which I'm trying to get to. And I have a test PW function here, which is where the buffer overflow is. So this is the part I'm interested in. So let's run it with run, and then give it a password that's 10 letters, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it gives me fail. Now info registers will show me the condition of the registers. And you have to get used to this. Oh, I needed to put in a breakpoint, pardon me. I wanted to put a breakpoint in at line 9. So notice here in my code, here is where the buffer overflow happens. That's where it takes 50 characters and puts it in a space where there's only room for 10. So at this point, I corrupt the memory. And at this point, I'm going to attempt to return from that routine, and that's when it's going to crash. So I'm going to break at line 9 before executing line 9. Break 9. All right, now I'm going to run again. And now I'm going to put in a 10-character password, all capital A's. And now it hits the breakpoint. Now I can do info registers, and I can see the internal registers in the processor. And what you're really learning here is the hardware of processors. You must understand exactly how the processor works in order to exploit it. The processor has registers stored on the chip. This is 32-bit code. So it's using 32-bit registers. You can see they are 8 hexadecimal characters. That's 32 bits. There's AX. A was the original register back when I started. in what, the 70s or something. With the 6502, there was only one register called A for accumulator. Now, then it was extended and extended again to get to 32 bits. So there's A, B, C, and D are the general purpose registers that can be used for any temporary storage. Then there is the instruction pointer, which is the most important thing when you're exploiting a machine. You want to gain control of the instruction pointer. The instruction pointer specifies the address of the next instruction to execute. So if you control the instruction pointer, you can redirect execution to an instruction of your choice instead of the instruction that the developer intended for you to use. And we're going to be doing stack overflow exploits. So these stack registers will also be important to us. ESP is the top of the current stack frame, and EBP is the bottom of the current stack frame. When you are in C and you call a subroutine, at the beginning of a subroutine, like test PW, it creates a new stack frame, which is a region of stack memory to be used temporarily only while this subroutine is executing, and when it returns, it frees it for reuse. So I'm currently in the test PW routine, so this is the stack of that routine. Now this routine doesn't have any variables except password 10, so it's only got a small stack going from 660 to 678. All right, so I'm going to examine the stack with this one, x12x $ESP. This will observe 12 words in hexadecimal format starting at the stack pointer. And notice my EBP is at 678. That is really important. Now I got to make my window a little wider to make this look pretty. All right, now we've got one of the major irritations of exploit development, which is that Intel is little endian. So when you look at this, it prints out this in the way you would naturally want a number to be printed out, with the most significant bits on the left, but they're actually stored the other way. So byte 660 is here, and this is 661, 662, and 663, and this is 664. So it takes a little practice to find your way around in this interface. So when it tells me here that the base pointer is 678, what that means, this is 670, this is 674, and 678, this is the 32-bit word beginning at address 678. So what I always do when doing exploit development is I put a breakpoint in after the overflow but before the crash, and then I do examine the stack, and then I always highlight the current stack frame like this. This is how you orient yourself. So these 7 words in memory are what's allocated to the current stack frame, and the next word right here is the return pointer. This is the address of code that's going to be executed. So if I can control that value, then when the subroutine tries to return, I will control the instruction pointer. Now a capital A is 41 in hexadecimal because it's 65, 64 plus 1 in decimal. And to get that memorized, and I think I do have the right hat on. This hat says 41, 41, 41. So this is what you look for, 41, 41. So these are the characters I injected. Now I put in 10 A's, and there was room for 10 A's. So the first 2 A's went here, the next 4 A's went there, and the next 4 A's went there. Now that's okay because my stack frame is this big. So I did not have an overflow. I just put it in the 10 spaces reserved for it. Then here's a counter to 10, which is used here to specify something in here, probably that, and so on. There's other variables in here. Oh, that's a carriage return. Anyway, it doesn't matter. So I put in 10 A's, it stored them without an overflow, and everything's fine. So now I want to set up an overflow. All right, so let's run it again. And I'll start it from the beginning. It's warning me I did not finish executing it. I hit a breakpoint and stopped, but that's all right. I don't care. And now I'm going to put in this long password, 4 A's, 4 B's, 4 C's, and so on. Okay, now it hits the breakpoint. Now I can examine the registers again with info registers, and nothing has changed. And this is why the stack still goes from 660 to 678. And this is why I mentioned C is such a dangerous language. I put in a much longer password, but it did not reserve more space to store it. It just shoved it in the space that's not big enough without caring. And that's what we're going to see. So I can examine the stack with the same command, x12x ESP. The stack frame goes to 670, 74, 78. This is the stack frame. That's the return pointer. And you can see I stomped on it. The 41 is A's, the 42 is B's, C, D, E, F, G. I've now overwritten it with GGHH in the return pointer. The program is okay right now, but when it proceeds and tries to return from the subroutine, it's going to try to resume execution at that address, which is GGHH in ASCII. So if I continue, it's going to crash and give me a segmentation fault. And what it's going to have in the extended instruction pointer, it prints here, although it doesn't tell you it's the EIP, that's what it is. It crashed with GGHH in there. Oh, FFGG apparently. A, B, C, D, E, F. Anyway, let me try on my fingers for A, B, C, D, E, F. FFGG. Okay, fair enough. So now I know how to control the instruction pointer. So what I usually do at this point is I try to make sure I can hit it accurately. So you've got a flag to put here, and let me just make sure I can. All right, so now we can put anything we want in the instruction pointer. We can choose an address. Now we wanted to run the win function. So if I do list 1 to 13 again, I was here in test PW, and then it's going to execute this return. And now normally this return would go back to main. In fact, here, just for completeness, let me put it all up here. All right, so when it hits this return, what the developer intended was it would go back up here to main and now print fail or win. But what I want to do is hijack that return operation to jump here and win. And I can do that since I control the return pointer. All I have to do is go to the start of the win function. Now I don't see addresses here. I need to get them in hex. So you do that with disassemble, win. Here is the assembly language, and it takes a little practice to get used to assembly language. This is what actually happens. You call put s here to print out the string, and these is how you move variables around between the registers and between memory, and then you have a call. And then you have leave and return, which is how it leaves at the end of a subroutine. But really, all I care about right now is that address. If I can cause instructions to move to that address, I can cause the win function to execute. So that's the address I need. And you can see, because I'm using exactly the same system that I did when preparing the project, that it's exactly the number up here. If you're using your own virtual machine or something, things will look different. But here it's exactly that address. So all I have to do is inject that code, and the easiest way to do it is with Python. So I'm going to make an exploit here. So I'm going to quit the debugger and create a Python file, and I'm going to put here the code that sends that exploit. So this sends A's, B's, C, D's, E's, and the first 2 F's. And then the next 4 bytes are going to be this address, and you have to put it in backwards because it's little endian. So to get to 5655, 56, 6E, I have to put each byte in reverse order, 6E, 56, 55, 56. And by the way, it's not necessary for this attack, but it is a good habit to get into to add characters after it to keep the total length of your attack always the same. This will prevent you from going mad. Because if you inject a certain amount of characters and find a crash, if you inject a different amount of characters, you might crash at a different statement. And so it's best to keep the total length of your attack always the same. So that's the Python code I'm going to use. Let me save that and then run it with exploit. All right. And so here it prints. Now in this particular case, the address is actually printable characters. That's usually not the case, but I could in fact have just typed it in this case. Normally you have non-printable characters, but that's what it looks like this time. So I'm going to make it exploitable, or make it executable, I should say, and then run it this way. And now I can run that attack into my vulnerable program, which was, I'm going to put it in a fixed string, attack pwd32. So now I've created a file here that is 41 bytes long. That is the characters that cause the exploit. And now I can feed it inside the debugger with this way. So I restart the debugger as we did before. Now before I did run and it asked me to type in the password from the command line, but here I'm going to put in a breakpoint at the same point. I can do this. I can run with arguments and take the data from that attack file I just created. So it will feed in that crafted password that includes the address of the routine I want to run. So now it will run here. It hit the breakpoint. I can do info registers again. And I can see that the stack frame now goes from 650 to 668. A little different than before, but not any bigger. So ESP and EBP, I can examine that with X, 12X, ESP. The bottom of the stack frame is at 668. So, whoops, I got to go here. All right, 668 is here. So that is the stack frame. Here's the characters I injected. And notice this address, 5655 56 6E. It sounds like I better mute people again. All right. And so that should be the address of win. So if I continue, it does in fact print you win. Then it crashes because I made a sort of sloppy attack. I did some collateral damage because I made this point to a valid address, but I did not fix this value, which should have been the saved EBP. So I messed up the stack and formed corruption, which caused it to crash later, but I did achieve my goal of executing that hidden routine. So I've not made a great exploit. I've made an exploit that does some good with some collateral damage, and as you get more skillful, you can avoid this. Now that is 32-bit exploits. All right. And so you've got some flags to find here. And then we got a 64-bit version of it to do, which I think I'll show you, and then I'll get out of the way so you can work on it. So I compiled a 64-bit version of it here with these commands. And so if I quit the debugger and I run this one, pwd64, again, if I put in a short password, it's fine. But if I put in a long one, let's try putting in 40. Again, I get a segmentation fault because it's exactly the same C source code. It has the same vulnerability, but it doesn't work out exactly the same way. So let's debug this one. And then list 1 to 13 again. You'll see exactly the same source code with the overflow on line 8 and the return, which is going to crash on line 9. So breaking at not before you execute 9 is the best way to go. And when I run it, I can now put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and examine the stack. Notice, by the way, the password address is a lot longer. Now, if I do info registers, the registers are much longer now. These are 64-bit registers and they have different names. It's not EBP and ESP, it's RBP and RSP, and the instruction pointer is here, RIP. So it's the same general structure, but everything is 64 bits long. So now I can overflow the stack. I'm going to inject the same thing I did before. So I run it again. Say yes, inject a longer string, hit the breakpoint, and now I'm going to info registers again. The stack now goes from RSP to RBP, so that's from 550 to 560. So if I examine the stack at RSP, okay, 550 is here, 560 is there, but the registers are 64 bits wide, so this is the stack frame. This is 560, 1, 2, 3, 4, 5, 6, 7. That is all treated as one 64-bit value, and this whole mess is the return pointer from 45 to 47. So if I continue, it's going to crash with a segmentation fault. All right, but it's not going to crash the same way where I can see the extended instruction pointer. It's in fact going to crash because it cannot put this other value in the extended EB pointer. Anyway, so it gives you a segmentation fault, and we can now pick a target address and inject it. So again, we disassemble win, and we get this address, which is exactly the one I saw before, 555547D0. So we can make an exploit file again. And it's just like the last one, except the values are longer. So this is that whole exploit, 00, 55, 55, 55, 47D0, this entire 64-bit value with each byte put in reverse order. So I make that executable and run it and create a text file with my exploit in it with this command. And once again, the text file is 41 bytes long. So now I've got it. Now I can run it in the debugger. So I break 9. And I run it, taking data from my 64-bit exploit. And now I can look at what's happened to the stack. Info registers shows that the stack goes from 530 to 540. So if I examine the stack, .530 to 540 goes here. And now I have this address here, 5555 and all that jazz. So again, now if I continue, I'm going to see you win, and then it's going to crash because of the collateral damage I haven't patched. So this is the place to get started. And something I was very happy, I learned this, I figured this out on the airplane when riding to DEFCON China. I'm able to put up a server that even gives you a debugger on the server. So you can exploit my server. I'm running a program, a version of this program on the server. So you can put in a string and hit debug, and it will run a debugger on my server and print out the answers. So you will see everything you need here. So here's the source code, although I've redacted some of the flags. And now you have to figure out how to reveal these flags by running the code. So it puts a breakpoint in, it runs with the input string you gave it, it dumps out the results, and then it continues. So this one, it's asked for a product key, and your product key was not accepted, but it didn't crash because I put in a short input. And you can put in a longer one. So if I put in, let's go, I was going to go Control A, C. Let's put in a longer one. Okay, there's a pretty long one. See if that's long enough yet. It looks like I'm going to have to be much bigger than 25. There's a 25 character area that something's pasted into. Here it took up to 100 characters, and here it crammed into something that only had room for 25. So that one caused a segmentation fault. So I injected a bunch of A's, and here you can see them. So if you look at this, this is 32-bit code. Here's ESP and EBP going from 20 to 48. So the stack frame is there. And I injected these A's. So at the, it's not incredibly clear to me why it crashed actually, but it crashed inside puts probably because I did some, because the null byte ran over and messed up EBP. So I've caused a crash, but I haven't yet controlled the instruction pointer. So I need to make it a little bit longer. By the way, one trick I like is to not even bother using the form. but to just manipulate the URL. So let me show you this. This is a good technique to use for this kind of exploit. Let me bring in a text editor. This is how I develop my solutions for this kind of thing. So AA wasn't long enough, so I'm going to put in more. B, 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 C, 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 D, 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 E, 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 E. There. Let's try that one. That's a longer string. And now the stack is here. ESP, EBP goes to C48. So that's here. And now I can see it's CCCC that hits, and here it tells me it crashes with CCCC in the instruction pointer. So now I control the instruction pointer. And by controlling the instruction pointer, I can reveal these flags. So give it a shot. There's more of those coming up. Like I say, this is the most important one in the whole course, in my opinion, is 202. If you do these, you will understand how memory corruption works in great detail. So I'm going to stop the recording and let people work for a while.